This is question 8 from the third CSAT sample paper. In this question we start with P lots of the letter A and M lots of the letter B, all written on a whiteboard in no particular arrangement, and then we can apply rules to this set of letters. We can take two A's and replace them with a B, take an A and a B and replace them with an A, or take a B and a B and replace them with a B. And we're asked for which values of P and M do we eventually get to just one A and 0 B's. So if you want to have a go at this question yourself, pause the video now. Okay, so one thing to note is all these rules reduce the number of letters, so it does look like eventually we're going to get down to very small numbers. But we need to work out in exactly which situations we get this particular state of affairs, so 1A and 0 B's. So one thing we can note is we could start with say just two A's or just two B's, and in each of those cases then we'd reduce to just one B, and then we can't do anything else because we don't have any rules for just one letter. So this doesn't have to happen all the time. Okay, so you might start playing around with these rules and see what happens. One thing you could think to yourself is, well, does it matter what order I apply the rules in? So if I start with some big collection of letters, and I start applying these rules in order to get to the this situation, does it matter how I apply the rules? Because it looks like it doesn't, because it suggests it just depends on P and M. But we might want to be confident of that. So you could answer this question by assuming the order doesn't matter, because they just asked for P and M, and you could get to the right answer. I will quickly discuss why the order doesn't matter. So something to note is, if we're checking the order we apply all the rules in, doesn't matter, well, let's just check it for any pair of rules. So for instance, what's the situation in which we can apply either rule 1 or rule 2? It's when we have two A's and a B. There might be some other stuff as well, but if this is here, we can apply rule 1 or rule 2. And we'll just think about the two orders that can happen. So we could apply rule 1, and that takes the two A's to a B. And then after that, we can only apply rule 3 and we get to 1B. Or we could apply rule 2 first, and that takes the AB to an A. And then once we have AA, then we just apply rule 1 and we get to 1B. So we get the same thing whatever we start with. What's the situation in which we have rules 2 and 3? That would be ABB. So if we do this, then we can apply rule 2 and the AB just goes to an A, and then we have to apply rule 2 again. It gets us to an A. And if we apply rule 3 instead, well, we just get to AB this way, and then again rule 2 takes us to an A. And then finally, rules 1 and 3, well, we could have two A's and two B's, because rule 1 applies to two A's and rule 2 applies to two B's. And either way, we just replace with a B. So if we replace the two A's, we get three B's, and then we can just apply rule 3 twice to get us to B. If we apply rule 3 first, then we get rid of one of the B's, we have AAB, and then we're in this situation. So if I call this star, we can see that always reduces to a B. So whenever I'm in a situation where I can apply one of two rules, it doesn't matter what order I do them in. And then we can think, well, suppose I'm applying a lot of rules in one go. So suppose, or one after the other. So I apply rule 1, then 2, then 1, then 3, then 3, and then maybe a bunch of other stuff. Could I reorder these and get the same result? Well, yes, because I can just swap any pair and then keep swapping until they're in the order I want. So I can reorder these into any order I like by repeatedly swapping. So suppose I want to have this. Suppose I want to apply rule 3 first, well, I could just take this rule 3 and move it to the front. So I'll swap it with this one, then with this one, then with this one, and then it's at the front. And then I can reorder the others in a similar way. So if I want to move this one later, I can keep swapping it, etc. Okay, so we see the order doesn't matter. So we just have some number of A's and B's. And the numbers are all that matters. So one other thing we might notice is if we have more than one B, we can just keep applying this rule, and eventually we'll just have one. So if we have three B's, then we use this rule, we have two B's, and we have two B's, we apply this rule, and we have just one B left. So the exact number of B's isn't really going to make a difference, because we can, if we have more than one, we can always reduce it to 1. Okay, so now let's think about the A's, which are a bit more complicated. Okay, so the next thing we note is it matters if p is odd or even. So p is the initial number of a's. And that's because if we think back to our rules, rule 1 lets us take any two a's and get rid of them. And the other two rules basically just eliminate b. So if a and b, we get rid of the b. If we have b and b, we get rid of the b. But this one gets rid of a's, and it gets rid of two at a time. So if we're trying to reduce the number of a's, say to 1, well, we're getting rid of a's two at a time. So what could happen? Well, using rule 1, if we have an even number of a's, then we just reduce them to all b's. But if we had an odd number, then there's going to be one a left at the end, because our rule for getting rid of a's only gets rid of two at a time. And then there's going to be the rest b's. So one thing to note here is that why is it okay to convert all the a's to b's? Well, it's useful because, as I say here, we know rule 3 gets rid of all the b's for us. So it makes sense to convert all the a's to b's as far as we can, and then just use rule 3 repeatedly to get rid of all the b's. Because we're looking for, remember, 1a and 0b, so very small numbers. We want to reduce the numbers all the time. Okay, so we've got two cases, odd and even, and then let's just see if either gets us to the right result or if we need any more information. So let's start with a even, and then we'll just call the number of a's p and the number of b's m, and think about what rules we're going to apply. Well, we said first we'll try to get rid of as many a's as possible, and we can actually get rid of all of them using rule 1. And then we use that p over 2 times, or half p times, because every time it gets rid of 2. And p's even, so that's fine. And how many b's are there? Well, we create 1 each time, so we have m plus a half p, lots of b. But then, if we just keep applying rule 3, then we get down to 0 a's and 1 b, and that's not what we want. So bear in mind, you might think, well, maybe I shouldn't have converted all the a's to b's, I should have stopped before I got to 0, because I know I want 1 left. But I can only get rid of 2 at a time, so there's no way of having an odd number of a's left. Another thing to note is, I said this reduces to 1 because using rule 3 just knocks off 1b each time, and once we get down to 1 we can't use it again. But this could be 0 if both m and p started at 0. But that also doesn't get us to what we want, because then there'd be 0 a's and 0 b's. Okay, so now let's look at a odd. So again, we start with p and m. And again, we're going to want to use rule 1. So now if we keep using this, because we knock off 2 each time, we eventually get down to 1. And then how many times have we used it? It's going to be p minus 1, which is an even number, over 2. And then there's going to be this many b's, but again we can reduce them to, well, I've said here use rule 2 rather than rule 3. So rule 3 would let us reduce these to 1b, but that's not what we want. We want 0. But if we go back and look at our rules, rule 2 just lets us get rid of a b as long as there's any a's there. And we have 1a left in this case, so we can just get rid of all the b's using this, and then there'll be no b's left, which is what we're looking for. So that means this always works. That's always what we're looking for. I.e., we just need p to be odd, and m can be anything we like. So this always works if p is odd, and it never works if p isn't odd. So this is all we need. So one thing to note here is, we could have seen this at the beginning just by looking at the rules. All of the rules, they don't change what are called the parity of the number of a's. Well, parity means oddness or evenness. So if we go back and look at the rules, this reduces the number by 2. So if the number of a's is odd, it stays odd. If it's even, it stays even. And these two don't change the number of a's at all. So if it's odd, it stays odd. If it's even, it stays even. And then because we want the number of a's to go to 1, that means that we expect to need p to be odd. If it's even, it can't go to an odd number like 1. But if it's odd, it can go to an odd number like 1. And then we just have to recognise that 2 and 3 allow us to get rid of all the b's, so it's only the value of p that matters.